Hello everyone, and welcome to the next part of the tutorial. This part of the tutorial will cover a data structure called the stack and allocation and deallocation of structs. Now, a stack is sort of like an array of items. And in fact, you could actually just use an array as a stack. The concept of the stack is whatever item you put in first comes out first. So you write to the stack and then you read from the stack, and the last item you put in is the first item that you take out. And to get an idea of this, we're going to go ahead and create a stack right now using an array. So let's do integer array stack, and then how about an integer count or an integer size, and we'll do equal 0. And then for the initializer, we're going to use struct stack extends array and struct. So there's the stack, the size. We're actually going to rename this to stack demo. Then private static method on init takes nothing, returns nothing, end method. Now we're going to create two new methods here, one called the add, or how about let's do write and read. So read and write. Stack method read takes integer I, returns nothing, end method. And stack method, let's change this to write. Write and read takes nothing, returns integer, end method. So for the write, all we are going to do is set size equal size plus 1 and set stack size equal I. For the read, in fact, let's do this. Set stack size equal I and then set size equal size plus 1. For the read, it will be set size equals size minus 1, return stack size. So all this will do is store the value into the array, increase the index, then for reading it will decrease the index and read the value right back out. So now for an example of how the stack works. In fact, for the read, how about we go call print red plus I to s stack size. So now we're going to call write, how about 5? In fact, let's do 1, 2, 3, 4, 5. So there we're just writing the numbers 1 through 5. And what do you guys think it'll display? Do you think it will display 1 through 5 in that order as we read them out? Or will it display 5 backwards to 1? Well, we're about to find out. So we go ahead and test them out. And it did not display anything, interestingly enough. So something got messed up here, I guess. So normally when you debug, you put little output things here so that you know where the code crashes, or if the code even starts. And the code started and everything, so it's running, it's just not printing. Oh, I know why, because we didn't call read. So let's read all the data back out. Okay, so there's the 5 reads, and now we're going to see what it displays. So let's do this. And it displays 5, 4, 3, 2, 1. So the last thing that goes into the stack is the very first thing that comes out. We wrote 5 last, so 5 came out first. So this is the actual order of the stack. It goes boom, then boom, 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 boom. And for other clarity, we'll say that the stack right now has 1. Now it's 2, 1, 3, 2, 1, 4, 3, 2, 1, and 5, 4, 3, 2, 1. Now the operations for normally adding and removing from a stack are called push to add and pop to remove. So if we actually rewrite this a bit, this would normally be called push, and this would be called pop. And we can go ahead and replace all that and pop. Now this is an array stack. It's static, it cannot be instance, it's somewhat useless, I suppose. There is another sort of stack, and that is the linked stack, and that's the one we're interested in. So now I'm going to get rid of this other variable here, and we're going to create a stack just using this array. We're going to use the null pointer, 0, as the first item in the stack, the thing that points to the first item in the stack. So let's change the code a bit. So when we push an item into the stack, first we need to make that item the stack pointer. In fact, we'll need another array here for values. But the first thing we need to do is, how about we change this to next to make it easier, is make the value we're passing in point to the first value in the stack. So we'll say next 0. And let's get rid of values. Oh. And then we don't even need the size here. So set next I equal next 0. Now the I we put in points to 0. Then we're going to set next 0 equal to I. So whatever was next was pointing to, whatever the first item was, I now points to first item. And then that 0 now points to I. And so the final layout looks like 0 to I to old first item. So it sort of has that stack structure in there. If we did it again, it would go 0, new I, old first item, and so on and so on. It keeps pushing in right here. And this 0 is sort of the stack pointer, stack ID. In this case, it's a static stack, so we can just use 0, but normally this would actually be an ID right here that represents the stack and is never destroyed. Now the pop is a little more tricky if we want to return the value in there. First, we need to create a local variable to get the value out, local integer I, and then that's going to be next 0. So that gets the first item in the stack. The next thing we need to do is set next 0 equal next I. So now 0 points to first item dot next, or I dot next. So the thing that I points to. So I is no longer in here. I is not there anymore. So it just goes 0 to next. Now we're going to go ahead and call print I, just to be clear here. And then we're going to return I down here. So it works the same way, except these aren't really values anymore. They're pointer values. They're like nodes for the stack, the things that are linked together. We could have another value here called value, if we wanted. And then we could add an array here for values. And then set values value equal to value. And then for the pop, we could return the value. So instead of this, we could go values I, and then return values I. And now we can actually push in like 1, 1, 1, 1, 2, 5, 7. We can repeat them, and then for our pointers we can just use this. Keep it like that. But for now I'm going to do 1, 2, 3, 4, 5 again to show that it works the exact same way. And in fact, for the pointers I'm going to show that they don't have to be sequential in any way. And how about we go 4,732. There we go. So this will now look like, if I write it out here, I'll just write out the last one. It'll look like 1042 points to 102, 2303, 5, and 4732. And the values they have are 1, 2, 3, 4, and 5. And we're reading the values out, not the pointers. So here we go. Test it out and see if it works. And sure enough, it did not work. Because I messed up right there. I put value instead of I. Try it again, and now it will work. Now it works. So 5, 4, 3, 2, 1. The 5 value works identical, except now these don't have to be sequential at all. Now these can be any values you want, and they will be linked together however you want. Now why this is useful is if we want to actually make an allocate and deallocate method. Let's go back here. We can now have, let's say, a counter, or count. How about allocated count equals 0? And now let's move everything into the struct. I'm going to rename a few things here, and we don't need the values anymore. We're now creating an allocator. So we're going to have a private static integer array recycler. How about we call that, and this recycler will just be a stack. And then we're going to have a private static integer allocated count. And this will be number of new thingies. So this will be the new IDs we get. So ID will start at 1, and then go to 2 and 3 and 4. And we'll get one of these new IDs if there's nothing in the stack. If there's something in the stack, we read from the stack instead. So if something in stack, read from stack. Now for the stack, for the push, all we need is this pointer value now. We don't need anything else. And for the pop, we again don't need the values, we just need the pointer value. So now let's make our first allocate command with private static method. So here we go. Private static method allocate takes nothing, returns this type. End method. So first let's check in the stack. Let's make a local this type this, and this is the special keyword right here for using struct pointers, and here's the this type we've seen before that translates into stack demo. So local this type this is equal to, how about we add a little if statement here. So we'll do set I equal to next 0. In fact, we'll just do next 0. There we go. We'll just keep it as is. So this will actually work perfectly as is right here. So we'll do local this type this is equal to pop. And we'll just pop it off. If this equals 0, so if the first item was 0, if it's empty, then set this equal to allocated count plus 1. And then set allocated count equal to this. So all we're doing is increasing allocated count by 1. And an easier way to look at it is to do, just for simplicity's sake, so allocated count equal allocated count plus 1, set this equal allocated count. Now if there was something in the stack, we're done right there. We can just go end if, because the stack already popped it off. And then we can return this. And there's the allocate command. For deallocate, private method deallocate takes nothing, returns nothing, end method. Notice it's not stacked, so it gets the this keyword. All we're doing here is call push this. And now it gets thrown into the recycler. So let's try it out now. We'll have a new instance. We'll say local this type this is equal allocate. Then we'll call print I2S this, and then we'll call deallocate. And the deallocate again is this.deallocate, or deallocate this. The this is inferred. I don't need to type it because it's a special keyword, so it's nice like that. That's why you always do this keyword when you're referring to struct pointers. Now we're going to save it. Oh, I forgot to change my variable names, didn't I? Okay, let's go ahead and change all those. Recycler. Okay, save it and try again. And there's the 1 that we allocated. Go ahead and deallocate that, and then reallocate it again. Set this equal allocate. It should show us the 1 again, because that's the first thing in the stack. Oh. And there's the 1 again. So the stack and recycler work beautifully. And that is literally how allocation deallocation works for structs. Now you have the other methods I talked about, the create and destroy method. All those literally do is may take arguments for initialization and whatnot, but you just literally do this. Equal allocate, do some initialization, like create units, return this. And then destroy, call deallocate, do some cleanup like removing handles, and then that's that. And then we can change this to create, destroy, create, and then we can add another destroy down here if we want. And there we go, fix the typo. Okay, so we've created our very first struct with instancing. Now this can be improved a little bit. Normally you do not have these push and pop methods in here. They are what are called inline, so all that means is delete them and put them in here. And we're going to change I into this. So all that does is pop it off, and then this will just read from the first thing in the stack. So if you notice here, I saved a few operations for when it's a new instance. And for when it's not a new instance, it's the same amount of operations. Then there's yet one other thing we want to be able to do. What happens if someone deallocates the same pointer 2 times? It gets thrown into the stack 2 times, and then everything breaks. So what people normally do is we use the debug keyword. That means this line will only work, will only be there when debug mode is on. And if you remember debug mode up here, debug mode, right now it's on, so it'll be there. But if it's off, then this line won't be there. Now, what's normally done here, debug set recycler, this equal -1. So this is an invalid pointer, and that means it can never ever happen normally. So what we can do in the deallocate method then is go if recycler this equal -1, then return. And then we can even go, and this should have debugs in front of it, shouldn't it? Debug end if, and we can even display an error message or something. Debug call display, let's use print. Attempt to deallocate struct instance more than, or how about attempt to deallocate null struct instance? How about that? So there's our little error message, and now if it can't deallocate, it'll get rid of it. And let's go ahead and inline the deallocate method. Yes, I put the deallocate method inside of the allocation, didn't I? So, and let's put the allocation here. So now allocation, that's the proper line. I was being weird before. Let's get rid of that. Get rid of all the comments here. Get rid of this. Get rid of this. And this. And now it's actually looking pretty good. So we have our proper allocation here. And now we have our proper deallocation here. And everything will work beautifully once I save it, with hopefully undeclared variable I. This. Now let's save it. Ha! So everything now works beautifully, and this is how actual allocators and deallocators look for structs when they're designed nicely. If you work with Sevian's allocate module, which is somewhere in here, alloc, if we go ahead and look at that, oh, it's somewhere in here. There it is. Alloc. Scroll down a bit. So we look in the allocate method. This looks familiar. Except here is also instance count overflow. So instead of allocate count, it's normally called instance count. I'm actually the one that came up with these standards for naming your instancing, because I was the only one at the start crazy enough to do all this by scratch. But normally you have an instance count overload. Remember, it can only go up to index 8191. So Sevian here screwed up a little bit since he's only using up to 8190. He's wasting one index. And then here, create a new index. Here's the recycler. And why he has two lines here is because he's reading the first instance here instead of up here. And then deallocate should look familiar. There's the original two lines we had, and there's the not equal one thing. So pretty standard allocation. There are a few optimization things. I had initially written them out. So one of them is set this equal to allocate count plus 1, set allocate count equal this. So this just cuts down on the global reads right here. Instead of a few more global reads, you have a few less. Globals are slower to read than locals are. So that's why this is done. Then we can add in the little overflow check, debug if allocate count equal 8191, then debug return, debug end if, and let's throw an error there too. Debug call print overflow or something. And then it saves undeclared variable allocate count. Probably need to fix, oh, one more. I see it. And return 0. How about that? Okay. And normally what I actually do is I'll do 1 divided by 0 or something like that. That way it crashes the actual application and stops it, because if it's already broken at that point, you might as well stop the entire map and fix it. So here, why don't we go ahead and do something like debug set this equal 1 divided by 0. There we go. And now these two things will crash it if there's an error, and that'll be the end of that. Most people won't crash it, but that's kind of the standard I'm setting now, so follow that one, because if your map's already bugging out, people aren't going to want to play it anyway. So just end it there, that way you don't get spammed with these messages. And then you can even go further with debugging, have something like a debug private static boolean enabled. So then you can go if, and we'll set that to true. So you can go debug if not enabled, then debug return 1 divided by 0, debug end if. So this will stop more messages from spamming and will stop all allocation from here on out. And then we can go debug if not enabled, then debug set this equal 1 divided by 0. We don't even need this return here anymore since we're crashing it right there. And we can also do debug set enabled equal false when an error occurs, and debug set enabled equal false. How about we just do debug set this equal 1 divided by 0. So now our allocator is completely done. And normally these should go into a module. And then you can just use the allocate and deallocate methods, and these can all be private inside the module. And you have all your nice debug protection and so on, and then you can just reuse the module. So let's go ahead and make the module really fast. You could use Sevian's but it's not as nice as this one right here, so just use this one. It's better. And module. Now let's go ahead and paste all the code in there for deallocate and allocate. Ooh. And then we can just implement the module at the top. And now it can be used. Oh, I probably need to make these public now, don't I? There we go. And it works. So now you should be able to create a struct from scratch with instancing and so on, and destruction and everything. So what does a regular vjass struct look like? How about we take a look at this? So tester end struct. And let's comment out all this code so it doesn't get in the way. We can find this easy. So how about we do method check takes nothing, returns nothing, end method, and throw a syntax error in there. That way we can look at the surrounding code. So if we look at the surrounding code, okay, let's do this then. Struct tester2 extends tester. When you don't have a struct that extends an array, it's a regular vjass struct, you can extend other structs. I do not recommend this because it creates what are called trigger evaluations whenever you destroy a struct. And those have massive overhead. They are not like function calls at all. So let's go ahead and do this now, and then we'll throw our syntax error in there. And take a look. And is apparently not going to generate the code with the syntax error in there, so we have to get rid of that. Okay, so how about we create a function, hi, takes nothing, returns nothing, then we'll throw a syntax error in there and see if it'll generate the code for us, so we can look at it. And how about we create a tester? Okay. Okay, now it created the code we want, I believe, somewhere. Oh, here we go. It's the stuff we want. So right there. Already we're seeing that it's creating a few more variables. So si tester f, that looks like a scalar variable, which is a non-array variable that points to the first value in the stack. And that's pretty similar here. If s not equal 0, then pop it off the stack. Else create new instance. So equal +1, set this equal that. This is different from the normal vjass helper because Cohater did this, so it's actually better than the regular vjass helper. Now if you look here, this is not a debug if. This is always enabled, so that's already... Well actually, hold on. Let's get rid of debug mode. Okay, let's go back up here. Because I believe that should only be, yeah, right. Oh. So this is not a debug protection right here. This is always up. So right there's already a bad thing. And then type is equal 3. That's for polymorphism. And there's the -1 check. Now we go into the destructor of tester. If this equal to null, return. So null is, you can compare them to null or 0 for integers. It doesn't really matter. You should use 0. So that's if you're trying to do a null integer right there. Null, 0, which you shouldn't be able to do. Then here it's comparing it to -1, which is the check from before. Then return. Then we have the set farg this. This is for trigger evaluations, for passing arguments to those. And right here we have the onDestroy, which is a little bit famous. Nobody really uses it anymore, but this is the polymorphic destroy method. So when you deallocate, onDestroy is called, always. The destroy method is not called onDeallocation, only onDestroy is. And trigger evaluations, as I said, are much slower than function calls. So this is why the polymorphism isn't really worth it right here. This is only open when a struct extends another struct. So I did the extension on purpose so that you could see this. And then here we have the push. Then similar stuff down here, type, etc. And no deallocator. That's interesting. As you see, it just chains off the basic allocate. So these extra protections here shouldn't actually be there because he should probably be just crashing the thread. But it's nice that it does chain off. It doesn't create a new instance for every single struct extending another struct, so that's good. So that's a look at standard structs. Oh, but just use this struct instead, and we should probably add a little check in here for 0. So debug if this equals 0, then... And how about we just do it here? Or this equals 0. Then do all that. So, that is struct instancing in a nutshell, as well as how stacks work.